Welcome to the new fortnightly RI Science podcast, where we bring you thought-provoking lectures from some of the world's sharpest minds. This week, space law and politics expert Jill Stewart introduces NASA Aerospace engineer Anita Sengupta, one of the leading engineers who developed the entry, descent and landing system for Mars's Curiosity Rover. Anita walks us through Curiosity's incredible journey to the surface of Mars and looks at the future of Mars exploration.
Thank you. It's a real pleasure to be here, and it's great to see such an amazing turnout, although given the speaker that we have tonight, I'm not particularly surprised. So Dr. Anita Sengupta is an aerospace engineer. She's research associate professor at University of Southern California, where she also did her master's and PhD. She's currently project manager for the Cold Atom Laboratory, or CAL project, which is set to launch to the International Space Station in June 2017. Where it will be used to study quantum gases in the microgravity environment. I come from a political science background, so these hard science terms intimidate me sometimes, but it sounds amazing. She was also lead system engineer of the team that developed the supersonic parachute system that landed Curiosity on Mars, and that's the topic of tonight's discussion, is Curiosity and our future on Mars. So it's a real pleasure to introduce Dr. Sengupta.
Thank you. Thank you for the introduction. Thank you for coming tonight. It's a real pleasure to be here. I want to talk to you about some of the fascinating engineering challenges that we've faced in the development of the Curiosity mission. So I'll talk a little bit about the challenges of landing on Mars and the challenges specific to the element that I worked on, which was the supersonic parachute. In terms of giving you a little bit of background about myself, I'm actually originally from the United Kingdom. I was born in Glasgow. I have no accent now because I moved to New York when I was a small child. But I spent, I guess, the first 2 to 3 years of my life here in the United Kingdom, and then moved to the United States, which is where I did all my education and my schooling and where I now currently work. In terms of my story, another British aspect is that when I was growing up as a child in New York, I watched an amazing science fiction program on public television known as Doctor Who. And ever since a small child, since the age of 6, I watched these reruns, and my doctor was Tom Baker, actually. And I was so fascinated by this alien who actually had the ability to solve all problems by using his brain, right? Using his willpower, his brain, his compassion, and his humanity, even though he wasn't human. And so growing up, I felt as though that was a wonderful influence for me, and I actually aspired to be able to be something like him, which was a scientist, an engineer, a brilliant person being able to solve the challenges. And so that's kind of what motivated my interest in engineering and in space exploration. So that's kind of an interesting aside, and I'm still a huge Doctor Who fan today, and I attend conventions in the United States on the topic. But I always knew I wanted to be involved in the space program. And so what I selected was to be an aerospace engineer, and so I studied aerospace engineering for my undergraduate degree, and then I continued to do aerospace engineering for my master's and my PhD, and I did that out in California. And over the course of my career so far, I've worked for NASA for around 15 years, I've been able to work on a variety of different projects. The very first one was developing something called ion engine technology, or plasma propulsion. So my background actually is rocket science. That was also something I wanted to do growing up. And so we developed engines which are now powering the Dawn spacecraft. So if any of you are familiar with Dawn, there's 3 very high-precision, low-thrust, but high-efficiency engines which have taken our spacecraft from Earth to the main asteroid belt, looking at 2 very unique asteroidal objects, one Vesta, one Ceres. After I worked on the development of ion engines for several years, I decided to do something completely different. I was asked if I wanted to work on the next mission to Mars, which was the Mars Science Laboratory Curiosity mission, and if I wanted to develop the supersonic parachute. And to me, that was an opportunity I couldn't refuse. How could you not want to work on a mission to another planet? So I did that for about 5 years. And that was successful. And then I decided to move on to a different challenge, which is my current challenge, which is developing a scientific facility for the International Space Station, which is going to launch in just under 1 year, actually. But what I wanted to start off tonight is to talk about how it was so difficult for us to be able to land a rover, basically the size of a small car, on the surface of Mars, which is billions of miles away. And so obviously I'm a little bit biased since I worked on it, but it was probably one of the most fascinating engineering feats in the past couple of decades. And so we've been successfully driving the rover around on the surface for the past almost 4 years now, collecting science data. And I'll talk a little bit more about the rover mission in terms of what its science is and what it's collected to date, but I wanted to focus a little bit more about the entry, descent, and landing cycle, and also why is it that we explore Mars. And so the obvious question to ask is, why are we interested in Mars? What's fascinating is that when the solar system first formed, planetary scientists actually believed that Earth and Mars were very similar to each other, both in terms of having a thick atmosphere and also having water on the surface. But over time, the two planets have evolved very differently from each other, where Earth still has a very thick atmosphere, it's almost 3/4 covered in ocean, whereas Mars is very dry, dusty, a very thin atmosphere, and no appreciable water on the surface. And so the way we can understand how the planets evolve is actually by sending spacecraft there. Spacecraft to orbit around the planet, and then also spacecraft that deposit landers and rovers to explore and make scientific measurements of the surface. And so that's the reason why we explore Mars from a scientific purpose. But the second reason, of course, is that at some point in humanity's future, we're going to want to live on somewhere other than Earth. And Mars is actually a relatively nice place. So we want to be able to learn as much as we can relative to other places in the solar system. But we want to be able to learn as much as we can about the planet from a scientific perspective, so we can understand what the properties are on the surface, what the composition is like, can we possibly access water, what the radiation environment is like. But we also have to develop the engineering technologies to be able to land a human-sized payload on the surface of the planet, as well as technologies to be able to survive on the surface of the planet. So those are the two reasons why we explore Mars. But first, I'll test some of your knowledge of as would we one day live on Mars. So who thinks that the day on Mars is shorter than the day on Earth, by a show of hands? Longer? Slightly longer, yes, you're right. So it's a little bit longer. It's 24.6 hours, which means from a human circadian rhythms perspective, it wouldn't be that challenging to be able to acclimate yourself to a slightly longer day. And actually, our engineers at the Jet Propulsion Laboratory who operate the rover do just that. They're always shifting their time in terms of going from 24 to 24.6 hours in terms of what their operational shift is on the ground. Now, in terms of gravity, it's about 1/3 the gravity of Earth. And the reason for that is that the planetary body itself is much smaller, therefore the gravitational force, the gravitational attraction, acceleration, is much lighter. So even though 1/3 g isn't good for a human body to be able to deal with, it's still much better than 0 g that, for example, we have on the International Space Station. Now, from a temperature perspective, the temperature on Mars, although it is cold, especially in the nighttime, in the polar latitude regions, in the wintertime, it actually does get relatively warm. 5 degrees C is actually a very common California winter, for example. So from a temperature perspective, it's also much better to be on Mars than in the vacuum of space or on our moon. So for these reasons, actually, it's not a bad planetary body to think of for future colonization of human beings, for example. Now, the big problem with Mars, of course, is that the atmosphere is very thin. It's only about 1% of what the atmosphere is here on the surface of the Earth, which means that if we do live there one day, we would have to be in a pressurized environment or pressurized suits for the surface of the planet. And then, of course, the atmosphere is not made out of air, which is primarily a mixture of nitrogen and oxygen, but it's made out of CO2. And we can't breathe CO2, so if we do in the future go to Mars, we would have to either come up with a way to turn CO2 into oxygen by splitting it up or bringing our own oxygen supply with us. But in terms of a future destination, for these reasons, Mars is feasible, it is practical, and it's also the closest planet to us. So then the challenge becomes being able to land something on the surface and be able to survive on the surface for extended periods of time. Thinking back to the geological history on Mars, Mars actually had a very, very ancient geological past. And the picture that you see on the upper right, Olympus Mons, is an extinct volcano. And it's actually the largest volcano in the solar system. It's actually, yes, 3 times as high as Mount Everest. And the reason for that is because at some point in the planet's past, it did have a lot of volcanism. But now that volcanism appears to have stopped or doesn't appear to be present, and we don't really understand why. Perhaps that's correlated to the reason why the magnetic field was lost, why the atmosphere is lost, we don't know. And so we send spacecraft to make measurements to be able to answer that question. And that's actually one of the primary reasons for the InSight mission, which is launching in 2018, which is actually going to carry on board a seismometer to make measurements of Mars quakes, if there are any still present. Another fascinating feature is Valles Marineris. It's actually a scar that goes across the center of the planet. And we like to talk to it as being Mars's version of the Grand Canyon. And it's an impressive, impressive feature. It's actually roughly 6 times as deep as the Grand Canyon. So what this means is that at some point in the past, there were appreciable water flows on the surface, but now they're gone, and we don't know why. Was the water completely lost? Was it stripped away and taken off into space? Or is it still frozen in the subsurface or in the polar regions of the planet? So Mars actually has 2 moons. It has Phobos and Deimos, and the reason why they look so strange and sort of potato-shaped is because they're relatively small, and they haven't compressed into a spherical basically structure under their own gravitational force. So they're probably captured asteroidal bodies that currently orbit the planet Mars. But one potential architecture or use of these moons is to use them as a telecommunications relay point, right? Where you actually set up satellite dish, you could think of, on the surface of these moons so that people or rovers on the surface would communicate to a constant telecommunication source on these moons, which then communicates back to Earth. That's another way of doing it. That's a potential architecture that you could use. And we also think there may be materials that we could mine from these moons, whether it be minerals that are useful to us for construction or even water for future surface missions. But another important scientific finding is related to water on Mars. So I kind of gave it away, but we have found water on Mars. As the Phoenix lander was coming into land, which was landed in the mid-2000s, its engines were pluming towards the ground, kicking up all the dust in the soil and exposing this white region beneath. And what this actually is salt water ice. So it's like a brine. So we know that closer to the polar regions, there actually is a lot of frozen subsurface water, which is important because that means future human colonies could use it for drinking, washing, growing plants, that type of thing. So this picture that you see here, and here, are pictures of water which is actually seeping out of the cliff faces on Mars. Because Mars is rotated on its axis, as the planet goes around the sun, it heats up and it cools down. So if there are frozen subsurface aquifers, they can melt and then seep out. And that's what we see here is seasonal flows coming off the sides of these cliff faces. So this, once again, is a really important finding because it means that there is water. It means that there is water accessible if we were to need it for future human needs. And it means that there could be stuff in that water. But until we actually are able to go sample it and take a look at it, we won't know. So that's another potential future mission where we would take a rover and have it access one of these sites so we could make compositional measurements of what's actually in that water. So the big challenge, however, for almost any mission that wants to land on another planet with an atmosphere is developing the technologies to be able to get yourself safely from exoatmospheric all the way down to the ground. And so landing on Mars actually has been a huge challenge. It's only been done 7 times successfully to date. The very first one was the Viking landers in the late 1970s, and you can imagine what an amazing engineering feat that was, right? We didn't really have sophisticated computers at that point in time. We also had very little knowledge of the Martian atmosphere. It was done again in the late 1990s with the Pathfinder rover, which was kind of a resurrection of the Mars program between the 70s and the 90s. It was done again in the early 2000s with the Spirit and Opportunity rover. Opportunity rover is still driving, actually, to this very day. So that was an amazing engineering feat to have something that could last for so long. And the Phoenix lander, which was a landed platform as opposed to a rover. Curiosity in August of 2012. And then we have 2 missions coming up. There's the European ExoMars mission, which is actually launching in October of this year. So I hope you guys are all familiar with that landed technology. And then the InSight mission, which is going to land to make measurements of Mars quakes in 2018. And then, of course, an interesting aside is that the Beagle mission, although it was lost when it initially came in for its landing in the early 2000s, we later found it. So we did find evidence of where it landed on the surface. It means that their entry, descent, and landing technology suite did actually work. Just unfortunately, I think the solar panels weren't able to deploy, and it wasn't able to communicate, so they weren't able to do science with it. But that was an important finding for the European Space Agency, that was successful. So in all engineering feats, we tend to build on our prior experiences, which are called our lessons learned, and we turn to improve our technologies from mission to the next mission to the next mission. And so what you can see here is the very first rover, which was the Sojourner rover, which was about the size of a Tonka truck, which is a child's toy. And then we moved to a slightly larger version, which I would say was the size of a lawnmower, which was the Spirit and Opportunity rover. And then most recently, we moved to the size of something the size of a golf cart or a small car. So as we increase the size of the rover, we increase the capability and the size of the scientific payload, and we increase our ability to drive over more difficult terrain, which may be more interesting from a science perspective. So what is the purpose of the Mars Science Laboratory mission? What is the purpose of the Curiosity rover? So it's actually to assess prior past, present habitability of the surface. So it doesn't actually look for life, but it looks for whether or not the building blocks of life, the environment for life, either existed in the past or currently exist on the surface of Mars. And we do that by making several scientific measurements, which I'll talk about a little bit more. But we're trying to assess the biological potential. We're trying to assess sort of the geochemistry of the planet. How did things form? Do they all form volcanically, or do they also form in the presence of water? And then we're also trying to assess what the surface radiation environment is, because one of the most difficult things for organics, as far as we understand organics, is their susceptibility to radiation. And so we know that radiation in space is quite bad. We know that radiation in deep space is very, very bad. So what is the radiation like on the surface of Mars? So we've never actually made that measurement until this particular rover. And so that's really important to understanding, is it so harsh that everything should have been destroyed based off of our current knowledge of organics, DNA, and radiation interaction? Or is it not so bad that, number one, maybe things can survive there, and also how much shielding do we have to bring with us to be able to support people living on the surface of the planet? So then the next question becomes, you're going to send this rover, where are you going to send it? You have to actually pick a landing site. And the way you pick a landing site is a combination of, can I actually land there, and where do I want to land? And so what we do is we work with the science community, the Mars atmospheric science community and the Mars geological science community. And they hash it around. They've argued for probably about 2 to 3 years as to the best site to go to. And they finally down-selected on Gale Crater. And the reason why they selected Gale Crater is because they believe, at least from orbital images of it, that it probably was the site of an ancient water body, whether it be a dried-up lake bed, dried-up riverbed, but they actually thought that. And where better to look for evidence of past life than in the base of a water body where sedimentary rock layers would form and you would see the history over time. Our challenge then was to ensure that the engineering system could land there accurately. And from a scale perspective, this crater geometry, we would have to land somewhere between this mountain in the middle and between the crater edge on the side, because if you didn't, you would either smack into the crater wall or smack into the mountain, and then there would be no mission. So this is Gale Crater. So this is the home of Curiosity now, and this is the landing site that we selected. And what you see here is sort of a black ellipse. And what this black ellipse is something called our landing ellipse. This basically, we've designed a system that we could land in an area which was 20 kilometers long by 7 kilometers wide. And that happens to be very tricky when you're trying to land in a space. We had to have the ability to have a precision so that we knew we could land in that area all the way from Earth going out to Mars. And so that drives the design of our engineering system. Because if you didn't, you have Mount Sharp here, which would be game over, and you have the edge of the crater wall here, which would also be game over. But because of the uncertainties in the atmosphere, because of the uncertainties in a whole variety of engineering parameters, you can't get yourself to a pinpoint location. You can only get yourself to this kind of ellipsoid location. The landing ellipse size for the 1976 Viking mission, 174 miles. We had to go from 174 miles all the way down to 12 miles. Apologies for going between English and metric units. So that's where the challenge was improving the accuracy of our landing system. Landing up through a planetary atmosphere utilizes the atmosphere to produce aerodynamic drag. So you come in at 13,000 miles an hour, you decelerate roughly from 13,000 miles an hour to around 1,000 miles an hour on a heat shield. You then decelerate from 1,000 miles an hour to around 250 miles an hour on a parachute. Then you actually can't go any slower on the parachute. You've hit terminal velocity. And so at that point, you actually cut the parachute away, and then you descend the rest of the way, slowing yourself down using retro rockets firing towards the ground. That's the way you dissipate the energy. And we had a total of 8 retro rockets actually going towards the ground. When we were around 60 feet above the surface, we started to lower the rover on a tether. This is called the sky crane maneuver. And we can talk about it might be good for a question and answer session if you want to know why we chose to do certain things that we did. But we primarily do it to increase the distance between those retro rockets and the surface of Mars, because they end up kicking up a lot of dust and sand. It also allows the rover to be the landed platform. So instead of carrying an airbag, which you have to carry all the way down to the surface, you just touch down on your wheels and you're ready to go. So what makes Mars actually nice from a landing perspective is that you don't have to carry as much propellant with you, because you can actually use the atmosphere to slow you down. So anyone has put their arm out the side of their car when you're going down a motorway and you feel the force on your arm, that's aerodynamic drag. So we use that principle to slow ourselves down, to take out roughly 99% of the energy coming in. The rest does have to be taken out using retro rockets, but the atmosphere does help you in that sense. The problem, however, is that, you know, when you rub your hands together, they get very warm. They get warm because of friction. We also experience friction with the atmosphere, and that friction with the atmosphere would make anything burn up. So we use a technology called a heat shield to absorb that energy so the rover inside of it doesn't heat up and doesn't get damaged. So that's the traditional architecture between how you land in a planetary atmosphere. And through all this, we have to manage our speed, manage our location, manage our altitude, and we have to know that. And we don't fly this back from Earth because the time delay between Earth and Mars is roughly 14 minutes in the worst case scenario. So this is all done autonomously by the spacecraft, by having knowledge of what the atmospheric properties are, and then making measurements using an accelerometer to tell it basically what its velocity is, and then going through a sequence associated with that. And so this is the overall architecture, and it's broken up into different phases. And so I'll talk a little bit more about the parachute phase, just because, you know, that's what I worked on for several years. So what is a parachute, and why do we use parachutes on Mars? So what a parachute is basically a textile device, and so it weighs almost nothing. It occupies almost no space, yet it generates a lot of aerodynamic drag. And so the parachute that we used for MSL was 21.5 meters in diameter. So that's 60 feet in diameter. It's huge. And the reason why the parachute has to be so big is because the atmosphere is so thin, which means a bigger drag area so that you can slow yourself down. And the reason why we like a lightweight device is because when you go into space, you usually don't have a lot of mass available to you, right? Otherwise, more mass, more propellant. So you want something which is as light as possible. And we use modern materials, which allow things to be incredibly strong versus more ancient materials. Like if you had a metal parachute or something, you wouldn't get much benefit from it. So that's what it is. And then also, because it's so thin, you can pack it into really tiny spaces. And so when we pack these parachutes, they actually approach the density of wood. So it gives you an idea of how tightly we can pack them, how little space they actually occupy in the vehicle. Yet when they open up to fill a room probably about 6 times the size of this. So this is a scaled version of a parachute. This isn't the full-size version for MSL, but it does have a very similar design. And then what you also note here is that there's an opening here. So this is called a gap. This region at the top here is called the disc, and this is called the band. And so the reason why we have a very specific parachute design is because of the aerodynamic environment that we found ourselves in. It's actually a supersonic aerodynamic environment, and it gets really unstable. And the way you control sort of the stability and the flow is by having this gap here, which kind of allows the atmosphere to flow through it so it doesn't collapse too much. So the other thing that is important is by having really strong materials. And so one of the strongest materials in terms of lightweight materials that we know about is Kevlar. So Kevlar is a very special material. It's a polyaramid fiber, and it has an incredibly strong strength-to-weight ratio. And of course, Kevlar is the same material which is used in bulletproof vests. So that gives you an idea of how strong it is. But this is more in a textile sense so that you can sew it and you can work with it. So then the question becomes, well, how do I design the parachute and test the parachute to make sure that it survives on Mars before I get there? And we actually do a lot of testing. That was one of the reasons why I took the job, because I love testing out in the field. And this was our very first successful test of the MSL parachute. We actually put it on a helicopter. We take it up to around 3,000 feet altitude, and then we deploy it. And this allows you to match the same load that the parachute sees in an Earth-based test as it would see in a Mars environment. The difference, however, is that the atmospheric pressure and density on Earth is much higher, which means that you don't have to take it up to as high an altitude. On Mars, the atmospheric density is much lower, so you end up having to have it go faster to match the same aerodynamic load. But the real challenge is that parachutes on Mars behave very differently. And the reason for that is that they deploy in a supersonic, low-density environment. So you see how it collapses and inflates and collapses and inflates. It actually starts to get a tear in it. So this is an example of a test that was done probably in the 1970s, I think it was. And they were able to take this parachute up to around 150,000 feet altitude on Earth, attach a rocket to it to get it up to Mach 2, and then deploy it to be able to experience the exact same conditions that it would see on Earth as on Mars. It happens to be very expensive to do these kinds of tests, so we weren't able to do that for MSL. So the space program budgets have gone down over the years. So what that means is that we can't just test everything how we would like to test it. We end up having to come up with much smarter, more cost-efficient ways of doing it. So what we decided to do was use our knowledge of fundamental physics, aerodynamics, and computer simulations to be able to understand how is this parachute going to perform on Mars? How are we going to make sure that it's strong enough? And so we first started off with a computer simulation. But when you do a computer simulation, the simulation is only as good as if it's correct, right? And so just by doing a simulation isn't enough. You have to validate your simulation. So what we did to validate the simulation is by building little subscale parachutes. This size parachute is roughly 3% of the size of the full-scale parachute. So if you build an identical model in terms of geometric shape, you should get similar aerodynamic performance. You can then put this model parachute in a wind tunnel at the appropriate conditions. There's actually wind tunnels where you control the density, where you can control the pressure, where you control the atmosphere, you control the speed. And so what we did was we built little subscale parachutes, put them in the correct aerodynamic environment, see how they behaved, made measurements of them in terms of the total load on them, and then compared it to simulations to validate the simulations. And so even though we did full-scale tests to do structural testing, we also did little subscale test to verify how it would actually perform in that difficult, dangerous supersonic environment. And we were successful, and of course we did land on Mars, so it did work. So I wanted to talk a little bit about Curiosity in terms of the rover. So you can see here, Curiosity is the size of a small car. Curiosity does also have a difference between the prior rovers. The prior rovers used solar panels for power. Curiosity uses an RTG. It's a radioisotope thermoelectric generator. So it uses the decay of plutonium-238, the heat associated with that, and converts it into electrical energy. And so what that means is that you have constant power, not just power when the sun is pointing on you. So that allows you to operate over longer periods of the day. It allows you to operate in places, further away from the equator. It allows you to do more science, basically. So that's the reason why we selected that particular technology. So that was different from this rover to the next rover. And then Curiosity, of course, had a very sophisticated mobility system that you can see down here, which allows it to traverse over rocks up to 0.5 meter in size without tipping over, without having any problems whatsoever. So once again, that big wheelbase is that big capability to take you to really interesting places. So the rover is a robotic geologist, and any geologist wants to be able to see as well as touch things, and so the rover does have eyes. It actually has a whole series of cameras. Some of those cameras are actually used for navigation, for hazard avoidance, so we do not drive the rover with a joystick. We give it a set of commands and tell it we want you to go there today. It has to do that safely, and it does that by collecting images with its cameras and doing, sophisticated algorithms to make sure that it isn't going to have a problem in terms of, going into a dangerous location or driving to an area that it couldn't drive. So that's what some of the cameras are for. And then others of the cameras are used to collect panoramic image of its surrounding, as well as microscopic images of the rocks that it's analyzing for scientific purposes. So one very important instrument is the SAM instrument, Sample Analysis on Mars. It's actually a mass spectrometer. So a mass spectrometer allows you to determine both elemental and molecular composition. So this is how we're able to look for organics. And organics, of course, are the building blocks of life, and this is probably it's a very heavy instrument, it's a very sophisticated instrument, and it does allow you to make the determination of whether or not organics are present. And one of the ways that it does that, and this maybe only Americans will appreciate this, but an easy bake oven. So it basically has a little oven that heats up samples, and when the samples heated up, they release a certain spectroscopic signature, which then you can associate with molecular composition, elemental composition. And so this is probably our most sophisticated instrument on Mars. And so we have another instrument which has a laser, and that laser also, it's called LIBS, laser-induced spectroscopy. This is a high-power laser, right? So if you were a astronaut on Mars, you probably would not want to stand in the way because it would burn a hole in your spacesuit, for example, because you have to use this laser to vaporize rocks, and when you vaporize the rocks, they then generate this spectroscopic signature, it's basically a plasma, which allows you to determine what the rock is made out of. So we have two ways of doing it, mass spectroscopy as well as laser-induced breakdown spectroscopy. So if you were on Mars, can you imagine not being able to touch anything? That would be terrible. Somebody wrapped your arms around your back. So Curiosity does have an arm. The arm has many different purposes, but it allows it to go and touch rocks, because if I put a tablecloth on top of this table, would you know that it was made out of wood? You wouldn't, right? You have to be able to remove the tablecloth to figure out what the table is actually made of. So what the arm has at the end of it is a brush, a drill, so it can actually interrogate the subsurface to determine what the composition is, not just the surface layer, which could be quite different because it could be deposited by winds and things like that. So the arm is very important for making measurements of soil composition of things, not just the surface, but the subsurface material. So we basically launched in November of 2011, got there around 8 months later. So in August of 2012, it was landing night, and it was nighttime, Pacific time in Pasadena, which is where we operate the rover from, and where a lot of the work was done. We had a very unique opportunity, this mission, where we attached a camera to the underside of the rover, so that during the landing event, all the way from entry, heat shield separation down to the ground, we could actually see what was going on. When the rover had successfully landed on the surface, its primary job was to send us telemetry saying everything's good, and an image of where it landed on the surface. And we're all anxiously waiting for this image to come down. And so this is the first image that we saw. So this is the shadow of the Curiosity rover. It looks like a transformer for anybody who likes transformers out there. And then what you can see here in the distance is Mount Sharp. And so it's pretty amazing, right? So it's hurled its way all the way from Earth to Mars and safely landed on the surface of the planet. So you can imagine we were all ecstatic that this happened, and it went off as planned. We landed where we wanted to land, and then we started our traverse towards the final location, making science measurements along the way. But as you can imagine, after landing that, we had a wonderful party. I think we were all out until 6 o'clock the next morning. And we were dancing and singing and stuff like that. Now, we have had some very important findings over the course of the past several years of driving around. We found the presence of phyllosilicates, which can only form in the presence of water. And we've also confirmed that the soil is actually neutral in terms of its alkalinity, which means it's not basic, it's not acidic. And that's very important from a formation of organics perspective, life forms perspective, because our existing experience on Earth suggests that neutral soil is much better for supporting life than acidic soil, which makes sense, right? But that's an important finding because other places that we visited on Mars have been acidic. So this is a location, because of its water body nature, where it was not acidic. So that was a pretty important finding. So some more things that the rover did: it scooped the soil. So it uses its scoop to collect samples that it then puts inside the instrument into the EV bake oven and gets it to work. And then we did a lot of using of our laser, our LIBS instrument. So now what does the laser really do? So what it does, it burns a hole in a rock. So this is the before, after loop. And when it burns the hole in the rock, it vaporizes the rock. It generates a spectroscopic signature that you can see here. And so each one of these lines is associated with a particular wavelength, and we know that that's actually a fingerprint for iron, magnesium, silicon. So this is sort of a elemental fingerprint for what the composition is of the soil on Mars that we analyze. So it's a very sophisticated but very robust way of determining what the composition is. And of course, you have to have a weather station. Curiosity also has a weather station. And so it has the ability to measure winds, pressure, and temperature. And so the interesting theory here, of course, is this is the diurnal variation, right? So it gets colder at night, warmer during the day, colder night, warmer during the day. So you can see the correlation between temperature changes, solar changes, as well as pressure changes. So this is another important measurement. You won't make much of this hash, but now we do have Mars surface radiation measurement. It's not as bad as we thought it was going to be. It still obviously is good for human beings, but now we have an ability to know what we have to attenuate if we are to send people on the surface. It also gives us a better idea of what Earth-based analog life forms could survive with that kind of surface radiation level. And the other thing to note is that having an atmosphere actually serves to attenuate radiation. So we can see variations in this radiation signal which actually correlate with the surface temperature because the pressure or the density of the atmosphere is changing during the course of the day. So this gives us a ton of information which we have never had before. And then another really important measurement is of organics. And so we did have confirmation of methane on Mars. And so methane is really important. It's an organic. It can only come from one of two sources, either geological or biological. So geological, coming out of the rocks, volcanic processes, and biological would be, cows produce methane in their gut, which is bacteria. So that's why we don't know until you have to make a more sophisticated measurement to get you an idea of whether or not it's biological or geological nature. So that we don't know. But having found it there is really important because methane has a very short lifetime, which means it had to have been produced relatively recently, meaning in the past less than a million years. So that's actually a pretty significant finding. So what is in the future? So the future is actually bright. We want to send human beings to Mars, hopefully within our lifetimes. And we need to enable the exploration of other worlds, and going to Mars will do that. So that would be the first stepping stone sort of for humanity going out into the stars beyond low Earth orbit. So in terms of the future, we would need to be able to live on the surface. We have to develop the technologies to land on the surface. We have to develop a rocket which will launch off of the surface. We have to develop habitation modules where we can survive the radiation environment, have the ability to maintain a pressurized environment for many, many years. So would you want to live on Mars? These are some artist conceptions of what it might look like. And I think it is a real thing of the future. And it's really just a matter of time and a matter of money and ingenuity for us to get there. And so in terms of what's over the next horizon, we don't really know, but we do know that there's several more Mars missions planned, so that's for sure. And also to point out, Curiosity took over 3,000 people, scientists and engineers, to design it, to build it, to test it, to operate it. 12 countries were involved that either contributed instruments or science investigations. All of the images that we take are returned to Earth almost immediately, available for everyone to look at. And a really interesting thing that most people know about is that that finding of water flowing on Mars was in October of 2015, and it was actually discovered by a student at Georgia Tech. So these images, which we make available, any scientist, any student can analyze and make it a part of their research program. So, yeah, because it's our rover. That's kind of how we like to say it. So I am happy to take questions for the remainder of the talk. I think we have 30 minutes. Thanks.
Thank you very much. So we're going to have some roving mics. I'm sure we might be able to hear you, but would you please wait for the mic if you do have a question? It's for recording purposes so that it's on the tape. So do we have any questions? I have one, but I'm going to. Okay, can we start over here? And while the mic is coming to you, I'm going to take advantage of my role as chair and ask you a question. So, of course, I come at this from a politics and law perspective, outer space law. And I love that you ended with who we are. I wonder, as a scientist working on the ground, how you feel about other entities that are starting to express interest in Mars. So, for example, the United Arab Emirates, China, also non-governmental organizations like Mars One. Do you guys see them as potential collaborators or as rivals, or?
So certainly the planet is not for anyone's taking, right? It's for everyone. So in that sense, I think the only way that we're going to be able to get humans to Mars is to do it as sort of a global endeavor, for sure. Both from a technology perspective, from a funding perspective, from a political will perspective. It's going to have to be kind of a universal endeavor. So the fact that more people are getting involved, I think, is a great thing. So, great.
You mentioned that the power source on Curiosity is radiation-based, which is an advantage over spirit and opportunity. But what do you think about the ethics of bringing a highly radioactive source with an enormous half-life onto a planet that has not yet been conclusively where life has not conclusively been disproved?
Well, it's not highly radioactive. So plutonium-238 actually has a relatively low radiation level in that sense. So you can actually kind of hold it in your hands if you wanted to. You shouldn't, but you can. So I think from that perspective, so we actually go to great lengths to protect the planets that we visit. So we actually have something called planetary protection, which is covered by all space agencies, just not the United States. So our biggest concern for planets that we may be visiting that may have potential life is actually contaminating them with biological contamination such as bacteria. So we actually go to great lengths to make sure that our spacecraft are clean, and we actually cook our spacecraft to basically destroy any bacteria or bacterial spores that are in them. So that is definitely, we're very cognizant of what impact that could have, and so that's one of the things that we do to make sure that doesn't happen. But from that perspective, not really. It isn't as bad as maybe as what you have been, you've heard or been told, but you can actually read up online as to what the levels are for plutonium-238 versus other radioactive substances, but it's actually pretty benign. And the reason why, and the fact that it is so benign means that it goes over a long period of time, like 70 years kind of thing, so it's generating only a little bit of heat. So you're just converting the heat into electricity by using a thermocouple, using the thermionic effect. But everyone has their own opinions. That's my opinion. Good point, though.
And come to this gentleman here. While the mic's coming over, just out of curiosity, this is not a very nice question, but do you have any sense of when you think there would be a manned mission on the cards?
So that's interesting. So I was just at a workshop this week where that was discussed, and so the timeline is for, I think it's mainly driven by finances and political will, but I think the timeline there they presented was like late 2030s, which isn't that far off.
Whoa,
but that would require obviously a lot of funding,
sure,
and international support to make that happen.
Yeah.
It wouldn't be done just by a single space agency for sure. But from a technology perspective, we still have a little ways to go, so that technology has to be developed first, which is an extension of what we've already done, but it is more difficult because, I guess one thing I didn't say is that, so when you're coming in to land initially, when you're coming in at hypersonic speeds, we actually used, and I did bring it here, I just forgot to mention it, so even though this ugly looking shape doesn't look like it would generate lift, it actually does generate some lift if you keep it at an angle of attack. So what was unique about the MSL mission is that we did have it at an angle of attack, so it had a lift to drag ratio, and that we had thrusters on the outside that were used to rotate the craft and then modulate its bank angle. So we were actually flying down like this as a means of increasing our downrange distance and as a means of actually reducing the total load that the vehicle would see from a mechanical perspective. So that's why I have my analogy of an airplane here. And so for a human entry, you would actually use like a lifting body trajectory like this. It would even be better than this one. So you'd have more lift to drag. And so that's a technology which we started with this mission, but we need to increase even further to be able to increase the landed mass. So for order of magnitude reference, you know, our entry mass is like 3,000 kilograms. A human mission to Mars is an order of magnitude higher than that. And it requires a larger space because you're not just carrying a rover, you're carrying people. So that's also another challenge that has to be developed.
We're going to go over here.
Two questions for you. As an aerospace engineer, what do you think the prospect would be of using aeroplanes or airships in the Martian atmosphere? And the other one is, we've seen things by Buzz Aldrin where he's thinking of people of my generation going on a one-way trip to Mars with no prospect of coming back.
I don't see the gentleman. Oh, I'm sorry. Okay, so the first one was airplanes on Mars. And so we actually are planning a helicopter demo for the Mars 2020 mission. So that's actually something that we are planning to do. So that's not quite an airplane, but it's kind of a, you know, it's kind of like an airplane. So it certainly is a thing that you can do. It would be a nice thing, like after you landed, you would have a little airplane that can go and do reconnaissance things and things like that. So that's what this helicopter is, and it's called, oh my gosh, Leonardo is the name of it. So it's going to be a payload on board the Mars 2020 rover. So it can definitely be done. Yes, the atmosphere is said, yes, you have to have a big wingspan, but it can't weigh that much. And then I think the second thing was, another thing you could actually do, which isn't an airplane, but you could use like a guided parafoil, which is more of a lifting parachute type thing, as a means of getting you more precise landing. So that's something that's definitely being studied. One-way trip, I think that's more of a catchy thing to make it sound like super risky, but we wouldn't do that. It just doesn't make any sense. So from a technology challenge, so my very first job, my initial background was actually in the development of launch vehicles and propulsion systems for launch vehicles. So my personal opinion as a aerospace engineer with a propulsion background is the technical complexity of a launch vehicle on Mars is actually far, far lower than a re-entry vehicle on Mars. And the reason for that is because you're using the atmosphere to slow yourself down. So you have all these bizarre aerodynamic effects that you have to take into account. You have the aerothermal heating, which you have to take into account. For a launch vehicle going through the atmosphere, you're dealing with 1/3 the gravity compared to an Earth-based launch vehicle. You're dealing with much lower drag compared to an Earth-based launch vehicle. So that's actually a much easier technology to develop. So I take issue with the premise that that's something we'd even do, because we know we can actually do that relatively easily compared to the other things that we have to do. So, but that's my opinion, because that's my background.
I've asked this question as well, and I've been told that governments would really not go one way because of the care of duty and that sort of thing. But when you have these organizations like Mars One, I think there's interesting ethical questions about what regulation we have over them and what they could sort of get away with. Do we have a microphone up? Can I go up to the lady in the blue sweater, and then I'll come down to this gentleman here.
Hi. In the Martian, obviously, there's the massive sandstorm that causes them to abort the mission. Is that something you could plan for during your EDL sequence, or was that something that would just cancel the mission?
So that was a flaw in the movie.
Oh, okay.
So yes, you actually do get high winds on the surface, but the density is super low, so you don't get the aerodynamic force that they showed. So it was the premise of the movie, which I think the author would admit that, you know, he didn't get it. He had to have some reason to have things go wrong, and that was one of them. So that's what that is. So we do know what the winds are. They are really strong. They can get up to 50 meters per second, but it's at 1% the density. So it's not that big of a deal. So it gets dropped down because of that. So not really, you don't have to worry about that too much. But you could also have a more stable platform. You would design it for your worst case scenario for sure. And then, so they actually, since you brought this topic, I'll say it. So my big issue with The Martian, the premise of The Martian, was, this is a really dumb one, but I just got annoyed with it in the first couple of pages. I love the book, don't get me wrong. I thought it was a great book, was that the fact that they would have no redundancy in their telecommunication system. That's ludicrous. So they had the one dish, it's gone, we're toast. That would not happen. So our little rover has a low gain antenna, 2 low gain antennas, and a medium gain antenna. It has the ability to communicate with orbiting assets and direct to Earth. So that's the reason why that premise, I think, was flawed. But it was the premise of the movie, so that's why they did it.
So weather isn't an issue on Mars for any mission?
Not in that sense. So this is an interesting aside, which is that the dust storms at altitude actually do affect the density profile on Mars. So we choose to not usually go in during dust storm season because it adds more variability to the density profile. If you don't know what your density profile is, you don't really know how you're going to perform. Your landing ellipse is going to get bigger. So if you can avoid the dust storm season, you would. And then the other thing that you could think about is that if you have dust particles, we don't know actually, like maybe they would interact with the heat shield material and potentially cause some havoc, but we have typically avoided going during dust storm season because of the variability in the atmospheric properties. Oh, and I would say that the rovers, which have had solar panels, unfortunately, that has deposit on the top of them, which then means their power over time decreases.
Hello.
Good question.
Sorry. Hi. I'm an aerospace engineer too, and I actually work on high-altitude drones. I was wondering, why would you use a helicopter versus a fixed-wing aircraft? And number two, what do you think about SpaceX's prospects of landing on Mars by 2025?
So I wasn't part of that engineering trade, but my guess is that it's driven by the science that they're trying to do. So if they're trying to do imaging in like sort of a fixed location, the ability to hover would probably give them a better science return. So that's my guess as to what it's driven by. And then from a controls, the people I know who are working on it are more in the controls area, so maybe they probably get more control over what it is that they're trying to image. So that's my guess. But it's also like a technology demonstration thing. And they also only have the need to go very short distances away from the craft, because it's probably battery powered, so they have to be able to come back. So it's more architecture dependent. It doesn't mean that you couldn't do an airplane, for example. I think you could. So, but then you would have a different mission architecture that you would probably go somewhere, stay there, and maybe never come back, right? Because you'd have to have enough power on board. So you always have to do that trade, right? So if your mothership has communications, your mothership has your power, and you're just going away from the mothership, coming back, that's different than if you are your own mothership. So. Oh, the SpaceX question. So I think that, so in general, the commercialization of space is fantastic. Getting private sector money in is fantastic. I think he's probably going to push it as far as he possibly can, right? Because I think he has the finances, or the company has the finances and the will to do it. There's a lot of challenges involved, and my guess is the company will work closely with NASA as part of that as well. So, but I think it's a great thing. So people ask me that all the time. So I mean, for sure, there's no reason why it should be restricted to one governmental body versus another one. I mean, you know, if you take it, for example, the aircraft industry, right? At some point, maybe it was all government, now it's not, and now people get to travel everywhere. So I think that's the way that you can commercialize space, by having more private individuals investing in the process. So,
can we come back up here?
Thank you very much for a fantastic talk. It was great.
thank you.
Considering how light the parachute and how small you can dense it to, why did you not make it much, 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 much bigger?
That's a good question.
And where is Curiosity going to go after the mountain?
So the reason why is, there's a simple reason why, is that we already made it much, much, much bigger from the last one. And so when you make a bunch of changes from a prior design, you do have a certain nervousness as to whether or not it's going to work. And so we knew, you start off with a set of requirements, so we knew what we needed. And so that size was actually what we needed to be able to be successful. The other reason why is that the way you deploy a parachute, on Mars at least, or supersonically, is you deploy it using a mortar, which means you push it out. And so there's only a certain size parachute that you can actually push out with a mortar. Otherwise, you have to pilot deploy it, which means that you have a little parachute which is deployed by a motor that then pulls out a bigger parachute. But because we've never done that supersonically, we didn't want to do it. So in order to be able to go with a bigger one, you probably would have to have a pilot deployed chute, but that technology didn't exist at the time. And so it's all about, you know, building on what you've done before. So if you want to do something completely different, then you have to spend a lot of money to do the completely different thing. That being said, there is a program which is ongoing now, which is called LDST, Low Density Supersonic Decelerator, where part of that program, which is a technology demonstration program, was to qualify a balut, which is a high Mach little parachute, which then could be used potentially to pull out a larger one in future. So that was sort of like follow-on technology development work that happened. But it's really driven by size, the ability to deploy it, and our experience base operating a certain aerodynamic regime. But this one was much, much bigger than the one we had done previously. So, and that was where we decided to call it quits at that size. Oh, what was about Curiosity? Where it's going to go to next? Oh, yeah. I mean, I think it has so much to explore, right? It's only just started exploring sort of the reaches of Mount Sharp, so it's just going to keep on exploring that region. So I don't think it's not going to leave the crater because it can't leave the crater because it can't get out from the crater. So it'll probably just explore more regions there, and will go for as long as it can. Because as long as it's surviving, and as long as it's able to collect the science data, it just collects more and more science data. And each location that it moves to, it sees something very different. And so the science data that comes as a result of that is also completely new. So even Opportunity, who's been driving around since whatever 2003, I mean, it's still going, right? And so it hasn't run out of things to see in its location. So I think there is far more science locations for it to see than it will last, given where it is.
Hopefully it'll outlast its sell-by date, but do you guys have an estimate of when
Well, so our mission life was only 2 years, so it's already exceeded that.
Okay,
so.
okay, incredible.
Hello. Early on, you had these bouncy balls, didn't you, where they came down and they bounced 27 times or something before they actually came to rest. Now you've got this sky crane thing. Have you got any other wacky ideas for landing on the surface of Mars?
That are wackier than the sky crane?
And if you were going to send humans there, what method would you use? Because obviously you can't decelerate too quickly, because then they would pass out because of the G's. So what do you think?
So in terms of the wacky thing that we did before was airbags, and so it did bounce around. And the reason why we picked that is because it was actually a pretty robust way of doing things, because you didn't really care about what your orientation was. The shock was absorbed by the airbags. So it was a good way of doing things, but airbags actually also have a technology limit. So the mass that MSL was too high for existing airbag technology. So then we're like, do we develop new airbags, or do we something different? Now the disadvantage of airbags is that you have to carry that mass with you all the way to the ground. You end up bouncing around all over the place, which gives you more uncertainty on where you're going to end up. Then you have to come out of the airbag. You don't know what your orientation is going to be, so then you have to have a mechanism which writes yourself to the orientation you want to be. All of that takes away mass from the science payload and puts it just on this landing system. So the Sky Crane landing system was actually more mass efficient, which means that you carry less mass to do your landing, more mass to do science. That's the reason why it's better. It's more complicated, which means it has more potential failure modes, which means you have to test and understand. But that was kind of the reason why we picked it. The other reason why we picked it in terms of going propulsively all the way to the surface was to increase the distance between those rocket engines were. Because if you take your garden hose and you fire it into a sandbox, what happens? Sand goes everywhere, right? But if you stand further and further away from the sandbox with your garden hose, less sand gets kicked everywhere. And so that's the reason why we use the Sky Crane mover, because it actually keeps you further away from the sandbox so that you generate less sand and stuff like that. So you could go, so another wacky way of doing it, which is something we have done before, which is you do go propulsively all the way to the surface, but then you have to do something to modify the rocket engine nozzles to reduce the amount of pressure from the nozzle, to reduce the amount of erosion that you see. Or if you were a human mission, which is probably what you would use, retro-propulsive all the way to the ground, you would have to create a landing pad, and so that landing pad would be made of something really solid. So that means you'd have to do it in advance, basically, so that you couldn't disrupt the vehicle by kicking up all that sand and things like that. But I'm trying to think, there's one more thing could you do, or you could also just cut off your engines, and you could maybe use sort of an aircraft system and glide into land. So that's another thing. That would be very wacky, which we haven't done yet, but which would be nice to do. And the thing that we're always pushing for is improved precision, so shrinking down that landing ellipse. So for a human mission, you'd pretty much want to shrink down the landing ellipse maybe to the size of this auditorium here. And the way you do that is by carrying more fuel on board, so you can fly out more of your errors to get to exactly where you want to go. And that video that I showed of the images towards the ground, of the final descent looking towards the ground, that was actually a technology demonstration for terrain relative navigation, where you're collecting onboard images, you're taking a look at the ground below and saying either I'm where I want to be, or I need to move a little bit to the right, to the left to get closer to where I want to be. So those are some things. So we always try and build in new capabilities with these missions so we can demonstrate them in a future one. And that is a capability which is actually going on Mars 2020, which is terrain relative navigation. That's already been baseline for it, as a result of us being successful with that demo on this one.
Great. I have a feeling we could go on all night, but
I might run out of juice.
Great questions. Thank you very much to the audience, and can you join me in thanking the speaker one last time?
Thanks for having me.
Thanks for listening. Next time, Adam Kucharski uses mathematics to take the luck out of gambling.